So we're going to start now. Last time we were discussing past paper questions related to atomic structure. Another a small thing that we're going to do is we're going to discuss uh, now what we're going to discuss. It's called ionization energies. Okay, it's not a small thing actually. You get very big questions on this on ionization energies. Uh, and before discussing ionization energies, the first thing we need to define what ionization energy is, especially what's the first. I mean, ionization energies are always written in the form of first, second, or third ionization energies. In ionization energies, you're removing electrons. So the first ionization energy is, okay, you're going to be asked about defining this. So it's always energy whenever you're trying to remove electrons. Think of an atom and you're trying to remove an electron like a hydrogen atom and you're trying to remove one electron from it, energy would be needed. Why? Because the electron would be very strongly attracted to the nucleus. So you would have to pull it away. You would have to make the electrons very energetic. You would have to give it energy. So remember, ionization energies are always they're endothermic. Okay, they're going to have positive signs. Energy would always be needed when you're trying to remove electrons. So first ionization energy is, by the definition for that, is that it is the energy that is needed to remove one more of electrons. As I remember, you don't remove one electron, you remove one, because one electron is so tiny that the amount of energy would be almost, I mean, you can't measure that. So you remove one mole of electrons from one mole of gaseous atoms. So you're removing one mole of electrons from each of the one mole of gaseous atoms to give you one mole of gaseous plus one ions. And measured under standard conditions. So standard conditions. So this is known as the first ionization energy, that you're trying to remove the first electron from an atom. What does gaseous atom? Gaseous atom means nothing. It just means that there's an isolated atom. For example, if you pick sodium atom and there's a single sodium atom not bonded with anything, so it would be in gaseous state. Okay, so think of an atom that's like, think of this atom over here. If it's not bonded, if it's an isolated atom, you're doing this in a lab, and it's an isolated atom, that means that it's going to be in gaseous state. Like for liquid and solid states, the atom needs to be bonded with the other things. So that's why you use the term gaseous atom. It's single isolated atom. So I'm going to pick the example of sodium. You're trying to remove one electron. So if you remove one electron, you're going to get one plus ion, gaseous, one mole of one plus ions, and one electron or one mole of electrons are going to be lost. So the enthalpy change for this reaction is going to be the enthalpy change of, uh, it's going to be delta HIE, the first ionization energy. It's very important to actually write gaseous atoms. And it's also very important to form gaseous. What I did miss was gaseous plus one ions. Okay, so it's extremely important that you write, uh, because you have to show that you're trying to remove an electron from an atom, just an atom that is not bonded to any other thing. So if it's not bonded to any other thing, then it would be an isolated atom and it's going to be gaseous. You're doing this in the lab. Sodium usually is not isolated. It's a solid metal. It's bonded with other sodium atoms. Okay, so ionization energies are calculated in the lab when you isolate atoms and you try to remove electrons. So this is first ionization energy. The second ionization energy is going to be exactly the same, So second ionization energy is going to be exactly the same. You can remember the definition. I've never actually. I mean, they ask for the equation, but usually not the definition for the second or the third because you can remove a lot of electrons. So once sodium has 11 electrons in total, so that means you can remove a total of 11 electrons from sodium. They're going to be 11 ionization energies. Uh, the first one is if you remove the first electron. The second one is that once the first electron has been removed, now you're trying to remove the second electron. So your starting point would be Na plus 1 and it would be gaseous. And you're trying to remove another electron and it would form Na plus 2 gaseous and another electron would be lost. Okay, so just on the safe side, I'm writing this definition as well. It's going to be pretty much the same. It would be energy needed to remove 1 mole of electrons, but this time from 1 mole of gaseous plus 1 ions, because the first electron has already been removed. So 1 mole of electrons from gaseous plus 1 ions, and to give you 1 mole of gaseous plus 2 ions. Gaseous plus 2 ions and measured under standard conditions. So measured under standard conditions. So that's the definition. It's the same definition, except that your starting point is different now. That you've already removed the first electron, now you're trying to remove the second electron. Okay? A lot of people make the mistake that they think the second ionization energy is when you remove 2 electrons together. You're still removing just 1 electron, except that you're removing the first has already been gone. I said it depends. अब उस पे आ रहे हैं, ठीक है? So we're now going to discuss factors that affect ionization energies. Okay, we're done with the definition. Uh, so I'll just because you can be asked to write different ionization energies. So what's the equation for for let's say the 12th ionization energy of? I mean, this is just an example. I'm asking for the equation of 12th ionization energy of chlorine. So what does that mean? What would be the equation? The equation is going to be that 12th is you're trying to remove the 12th electron. That means 11 electrons have already been removed. So chlorine would be 11 plus 1. Okay, you've already in the lab, you've taken a chlorine atom, you've already removed 11 electrons, and now you're trying to remove the 12th electron. So it's going to end up forming 12 plus ion, and 1 more electron is going to be lost. Okay, so every time it's going to be 1 electron that would be lost. Similarly, if it's the 5th ionization energy of, let's say, calcium. Okay, and remember to write the states. When you're writing the equation, you're going to lose mark if you don't write the state. It's a 5th ionization energy of calcium. That means 4 electrons have already been removed. So calcium is 4 plus gaseous, and now you're trying to remove the 5th electron. So it's going to be calcium 5 plus, and that would also be gaseous. So 1 more electron would be lost. Okay, so you could be asked to write different ionization energies of different elements, and you'll be asked to write equations for them. Now, moving on to the factors that affect ionization energies. Okay, I'm just writing I dot E. Usually it's not written as I dot E, it's written as in the full form ionization energies. But I'll be writing I dot E. Now, factors that affect ionization energies. For example, sodium has 11 protons. Let me draw an atom of sodium, and it has 3. So it has 3 shells. and a total of 11 electrons. 2 in the first shell, low, I mean, that means low energy, so that's close to the nucleus. 8 in the second shell, and there's 1 in the last shell. Okay, that is what sodium is. And what factors affect ionization energies? There are actually 5 factors that affect ionization energy. The first thing is uh, what makes it difficult or easy to remove electrons. The first thing is it's these protons over here. The protons are the ones that are attracting electrons. So if you have more protons, the electrons are going to be more strongly attracted. So if the positive charge in the nucleus is more, then the attraction for electrons is going to be much greater. So that's the first number one factor, and that's known as the nuclear charge. Or in simple words, you can call it the proton number. So it's pretty obvious, more protons, so there's going to be more attraction for electrons. So there's going to be more attraction for electrons. So it would be very difficult to actually remove electrons. More attraction for electrons, so higher ionization energy. A lot of energy would be needed. A lot of energy would be needed to remove electrons. ठीक है? Is this clear, Sanjida, Minahil, Bazga, Rida, is this clear? Usman?
Yes.
Achha, so that's factor number one. ठीक है? Then there are 4 more factors. Factor number 2 is it's called the distance, or you can call it the atomic radius. Or you can call it the distance of the electron from the nucleus. So distance is another factor. For example, so that's factor number 2. Like if you're trying to remove this electron is very far from the it's very far from the nucleus. So the attraction for, I mean, because the distance is greater, so the attraction would be lesser. As you move further away from the nucleus, the electron is going to be less and less attracted. If you're very close to the nucleus, the electron is going to be very, very strongly attracted. So that's another factor, that greater distance. So if you have greater distance, then there's going to be less attraction for electrons. Between the nucleus and an electron. So because of that, the ionization energy would be lower. So there's going to be lesser ionization energy, lower ionization energy, because the electron is further away from the nucleus. Now, the third factor. The third factor and the second factor are usually kind of interlinked, and this is known as the shielding effect, or you can call it the number of inner shells. So that's factor number 3. What that means is, and let me, if I can do this. So this is your outer electron and this is your nucleus. So there's the electron. The reason this electron is attracted to this atom is because the nucleus is attracting it. But there are shells coming in the way. And if there are more shells coming in the way between the nucleus and this outer electron over here, the attraction would be lesser. For example, if there's magnet and there are nails and they're getting attracted, and you put something in between, so the attraction would be lesser. Similarly, this is what's going to happen. So if the nucleus over here, this positive nucleus right in the middle, ठीक है, this positively charged nucleus in the middle. If there are lots of shells coming in, inner shells, lots of inner shells coming between the electron, we're trying to remove this electron and the nucleus. That's known as shielding effect. So the greater the number of inner shells, the less would be the attraction. ठीक है, Rida, Usman, Sanjida, is this clear? Minahil, that you have more inner shells? Less attraction between electron and nucleus. And because of that, the ionization energy is going to be lesser. So there's going to be lesser, or we call it lower ionization energy. Okay, that's factor number 3. Then you have a fourth factor, which is known as the effective nuclear charge. Or we can call it the net positive charge on the atom or the ion. Okay, so that's another factor. What that means is that if I'm trying to remove the first electron, okay, forget all the other factors. The atom is neutral. So overall, it's a neutral atom because the net or effective nuclear charge or the net positive charge is the charge because of the protons and the electrons together. So right now there are 11 electrons, 11 protons. So the effective nuclear charge or the total charge on the atom is actually 0. Once I remove this electron, the first one, now the net charge on the whole thing is positive. It's a positive ion. It's a positive 1 ion. Now the thing is, it's going to become harder to remove electrons because if the overall charge on the whole thing is positive, then it would be attracting electrons instead of actually losing electrons. It would be more difficult to lose electrons. And let's say we give it energy and we somehow are able to actually remove another electron. Here, let me. So we are somehow. So we are somehow able to remove another electron. Now the total charge on the ion is going to be +2. So the net effective charge on the whole thing is now +2. Now it's going to be attracting electrons even more strongly, even electrons from the outside. So it's going to become harder and harder to remove electrons if the net positive charge on the whole thing becomes more and more positive. So if net positive charge on the ion is greater, then it's obviously going to be more difficult to remove electrons. So it's going to be more difficult to remove electrons. Try removing electrons from +5. +5, it would be very hard because it would be very strongly attracting electrons. So it's going to become more difficult to remove electrons, and you're going to have a higher first, not the first, just the ionization. You're going to have higher ionization energy, whatever ionization energy we're talking about. So is this, Asasman, what I'm saying is, well, you're trying to remove electrons. You're constantly removing electrons. You have the first ionization energy, you have the second, you have the third, and so on. So imagine you're removing the first electron. The sodium, what charge does sodium have? 0, right? And you're trying to remove an electron. So the overall charge is 0. But if you're now try and think if you're trying to remove electrons from a sodium which has a +5 charge. This is the sixth ionization energy. You've already removed 5 electrons. you're trying to remove another electron. Now, in which case would it be very difficult to remove electrons? If the overall atom, the entire thing has a charge of +5, then it would be very difficult to remove electrons because electrons are attracted to a highly positive. I mean, the +5 would be very strongly attracting this electron, so it would be very difficult to actually remove this electron. Usman, did you understand this? So the point is, if you keep on removing electrons from sodium, okay, let's say I've removed another electron. Now the overall charge is going to be +3. I mean, that's the net charge. That's going to be +3. Why is it going to be +3? Because you have 11 protons, and now you have 1, 2, 3, 4, 5, 6, 7, and 8 electrons. So 8 electrons minus 8, and 11 protons plus 11. So the net charge is +3. So the overall positive charge on the whole thing, which is the effective nuclear charge, the net positive charge, keeps on increasing. And it would make it harder and harder for you to remove electrons, TK, because electrons would be very strongly attracted to the would be attracted. If this is highly positive, then the electron would be very strongly attracted to it. So it would be much harder to remove electrons. TK. Is this clear to everyone? Sanjida, is this clear? Rida, uh, Bazga, Minahil, is this clear?
Yes.
Yes.
That's a factor number 5 is as a factor number 5. That is subshells. Now, this factor, we're not going to discuss this factor right now. Okay? And it's not a very important factor because it doesn't really matter which subshell you're trying to remove electrons from. What matters is which shell you're trying to remove electrons. If the shell is higher, that means the electron is very energetic and it would be very far away from the nucleus. If the shell is lower, then that means the electron wouldn't be very energetic and the electron would be lying very close to the nucleus. Now, subshells doesn't really matter. It's not an important factor. And it only matters in a few instances, which we are going to discuss later on. So only matters in a few instances, uh, which we are going to discuss later. Okay, so we'll keep that. But just remember the first 4 factors, the ones that are more important. The fifth one is not as important. Okay, and we're not going to discuss fifth yet, not right now. Um, so 4 factors. Okay, just a quick recap. Protons, you have more protons, the electron would be very strongly attracted. So difficult to remove electrons. Atomic radius or the distance of the electron, if the electron is very far away, then it would be easier to remove electrons. Shielding effect, if the nucleus and the electron, there are lots of things coming in the way, lots of inner shells, then it would be easier to remove electrons. Effective nuclear charge, that if the whole thing, the overall charge of the entire thing is more and more positive, then it would be more difficult to remove electrons because the electrons are going to be very strongly attracted to the whole thing. So the first thing we're going to discuss now is, I mean, we have 5 factors, and we're going to talk about these 5 factors over and over again. So the first thing that we are going to talk about now is it's called uh, successive ionization energies. Okay, we're going to discuss each one of the factors, how they, I mean, all 5 factors usually play a role, except for the fifth one. Most of the time, it's all 4 factors play a role. So, what is successive ionization energy? Successive ionization energies is when you successively try to remove. So, when you successively try to remove electrons from the same atom. From from the same atom. So you're going to try and remove the first electron, then the second electron, then the third electron. So let's pick magnesium for magnesium has 12 protons. It has 3 shells. So that's 1, 2, and 3. So that's 2 electrons, 8 electrons, and then you have 2 more electrons in the outermost shell. Okay, that's magnesium. So we're going to talk, we're going to sketch a graph now. And the graph, one axis would be ionization energies, the other one would be the number of the ionization energy, the first one, the second one, the third, and so on. So this is the first. I'm just going to write 1, 2, removing the third electron, then removing the fourth electron, then we're trying to remove the fifth electron, sixth, seventh, eighth. You have 9, 10, 11, and 12. Okay, so that's 12. That's the number of the ionization energy. Okay, so in total, we're going to try and remove 12 electrons. This axis over here is the energy value. How much energy would be needed to remove electrons? Now, when we're trying to remove the first electron, okay, so think of this, we're trying to remove the first electron. And the 5 factors. The first electron is really, really far away. So from the nucleus, and it's shielded as well. Lots of inner shells. It's far away and it's shielded as well, and the net charge is 0 as well. So it would be actually very easy for you to remove that electron. So removing the first electron would be kind of very easy. Okay, so it's going to have a very, very low ionization energy value. Okay, so we've removed the first electron, that's gone. Now, once I've removed the first electron, the overall charge on magnesium becomes +1. Okay, is the first point clear? Bhaskar, is this clear? Minahil, Rida, Sanjeev,
Yes,
Usman.
sir.
Okay, so removing the first electron is going to be extremely easy. So what about removing the second electron? What difference is now there? The second electron is just as far away as the first electron. The first electron was over here. The second electron is also far away. It's in the third shell. So that's not a factor. It's also shielded. So that's not a factor. The only difference is that now you're trying to remove an electron from an ion which has a +1 charge. So the electron, I mean, it has an overall net positive charge now. So the electron would be kind of more attracted to the whole thing. So it would become kind of harder to remove this electron, but not very hard. So just slightly harder. Okay, so just slightly harder. So I'm going to write this down. That when you're removing the second electron, overall and net is the same thing. Net positive charge slightly it increases by 1. Positive charge increases. So only one factor is important. Distance and shielding and every other factor is pretty much the same. So net positive charge increases. So uh, ionization energy slightly increases because only one factor is in play. So we've removed, so we're going to try and remove the second electron. That's gone. So now we're trying to remove the third electron. Now, all of a sudden, there's going to be a drastic increase in ionization energy, a drastic one. So all of a sudden, there's going to be a very drastic. So all of a sudden, there's going to be a very drastic jump in ionization energy, and we're going to discuss why there's going to be a drastic jump in ionization energies because all of a sudden the third electron is very close to the nucleus. Plus, it's less shielded as well. I mean, this outer shell is gone. So the number of inner shell, so the number of inner shells are now fewer because the electron and the nucleus, there's only one shell coming in the way. So it's very close to the nucleus. So there are three factors in play now. One of them is distance decreases. The other factor is shielding decreases all of a sudden. And every time net positive charge is obviously increasing. So that's also making it more difficult to remove electrons. So third electron, there's going to be a big jump. Okay, is this clear to everyone? Yes or no? Is this clear?
Yes.
अच्छा अब उसके बाद what's going to happen is after that, once you've removed the third electron, the third electron is also gone. Now the third and the fourth and the fifth and the sixth and the seventh and the eighth and the ninth and the 10th. The only factor that's changing, I mean, this is the 10th, right? So now the net charge is plus 10. So the only thing that's actually changing is the net charge because the distance is the same. I mean, if you're removing uh, the third and the fourth and the fifth, sixth, seventh, so there's only one factor that matters because the distance is the same, your shielding is the same, only the net charge is actually continuously increasing. So till the 10th, let me mark where 10th is. The ionization energies would increase, but they're going to increase gradually. Okay? There's not going to be a drastic jump because only net positive charge is changing. So only net positive charge increases. So there's not going to be much of a jump here. Okay? Every time you're removing electrons, the distance and shielding pretty much remains the same. So you've removed the 10th electron. So all 10 electrons in total are gone. You're left with the last two electrons. Now, as soon as you start moving to the last two electrons, again, there's going to be a drastic jump. So removing the 11th electron, all of a sudden it becomes kind of difficult. Why? The same factor. That when you're trying to remove the 11th electron, all of a sudden you've changed shells. You're now much closer to the nucleus, so it's much harder to remove electrons. Plus, now there's absolutely no shielding, so they're directly attracted to the nucleus, so very, very close to the nucleus. So all of a sudden, 11th electron would be very hard to remove. And there's going to be very little difference between the 11th and the 12th. So the 12th is going to be just slightly harder to remove because of the net positive charge. So that's going to be your overall sketch of this is called your successive ionization energy sketch for magnesium. Okay, is this clear to everyone and the reasons clear? Yes or no? Is this clear?
Yes.
Asha, so the thing that matters, I mean, you must know, you must remember the reasons because you're going to be asked, okay, you'll be shown this graph and you'll be asked, okay, why is there a jump? Okay, what's the reason for that? You must know what's the reason. Whenever a shell changes, the distance automatically decreases and the shielding decreases and the positive charge is continuously increasing. So three factors make it harder to remove electrons. So this is the point where shells are changing. What information do you get from this particular graph? One of them is that you get lots of information from this graph. One of them is, I mean, the major two you get the valence electrons If you get the valence electrons, you also get the group number. So if you know the group number, you know whether it's a metal or a non-metal. You get, I mean, if you know the group number, you get lots of other information as well, like what type of bonding it would do. Because you're going to be asked questions like this. Okay, for example, you might be given this graph and you'll be asked whether this compound, let's say, call it X, whether it's going to form an ionic compound with chlorine or a covalent compound with chlorine. Okay, by just looking at it, you should notice that it has two electrons in its outermost shell. So that means it's in group 2. So that means it's a metal. So based on group number, if you're able to figure out the group number, you can figure out a lot of chemical properties of the compound. The other thing that you can figure out is the total number of shells. Okay, so this is shell number 1. This is shell number. This is actually the third shell. This is shell number 1. Then you have shell number 2. So all these electrons over here, that's shell number 2. And this is shell number 3. So these are one of the major things that you're going to get out of this. Uh, and sometimes a graph would not be given. You actually have successive ionization energies in your data booklet. Let me find. So this is your data booklet. Uh, so let me find successive. This one. TK, you're actually not successive. I mean, it is successive, but it's the first, second, third, and fourth ionization energies. The values are given in the data booklet. For example, if you look at magnesium over here, this is magnesium. So it's 736, 1450, 7740, and 10500. What you need to notice is because if the graph is drawn, then it's actually very hard to see to find the jump because it's. I mean, your eyes can clearly see where the jump is. The problem would be that if a graph is not given, that's when it would be slightly harder to actually. So if you're given random values like these, then then it's harder to actually see where the jump is. So I mean, but if you look at the value 736, 1450, and then all of a sudden it's 7,000. So this is where the jump is happening. So this is the point where the jump takes place. That means a shell has changed. The first two electrons were easy to remove, so they must be in the outermost shell. The third and the fourth electron are now inside, closer to the nucleus. So they're kind of harder to remove. So using this, you can figure out, for example, chlorine over here. Chlorine has 7 electrons in its outer shell. So the first 7 electrons, there's not going to be any jump. So you can see there's a steady pattern, 1260, then 2300, then 3850, then 5150. There is no jump occurring. If you look at some other element, let's say calcium, calcium is also in group 2. So right after removing the first two electrons, there's going to be a jump. So which is there, 590, 1150. First two electrons are easy to remove. Then all of a sudden it's 4940 or almost 5000. For sodium, I'm trying to find sodium. For sodium, the jump would be right at the beginning. Like removing the first electron would be easy. Then removing the second would all of a sudden become very difficult. Okay. Acha, so is this clear? What you need to do is, okay, there's a small assignment. What you need to do is draw and sketch the successive ionization energies of aluminium. Also try chlorine, lithium, and let's say oxygen. Okay, sketches like these. You can pretty much get the idea of the sketch. So try and send me, please try and send me the answers. Very few people are. Only 3 people, I think, are sending the answers. Everyone try and do this, okay? I'll be waiting for the answers. And I'll be messaging you if you don't send me the answers, okay? Okay, then we'll continue with this in the next class then, okay? If you have any questions, you can ask them now. If no questions, okay, so we'll continue tomorrow then. Okay, take care. Allah Hafiz. Sanjita, yes, you'll be asked to actually make graphs. We'll do past paper questions after this, okay? I mean, you'll be asked to sketch graphs. You'll be asked, a graph would be given and you'll be asked a lot of information about it. Okay, so it's both ways. चलें ठीक है, okay, take care.